We have started with the unit oscillations, and in a previous lecture we have seen what is a simple harmonic motion. So the simple harmonic motion is a motion in which linear motion of the particle in a back and forth direction, in which this restoring force is directly proportional to the displacement, and it is always directed in opposite direction to the displacement, or this force is always directed towards the mean position. So this is called as a simple harmonic motion, and in this lecture we are going to study what is the equation of the motion of the S.H.M. So let us first see why we calculate the equation of the motion. So whenever you are dealing with the physics, so you try to evaluate the equation of a motion for any particle or any system of the particles, because once you know the equation of motion of any system, then you can calculate all the physical quantities which are required in a physics. Like you can calculate the velocity, you can calculate displacement, acceleration, energy. So once you know the equation of the motion of any system, then you can calculate all the physical quantities related to it. Generally the equation of the motion is the relation between the force and the momentum. Now according to the Newton's second law, so this force is equal to dp upon dt, or this force is equal to m into a. And now we know that this force is a restoring force in the case of the simple harmonic motion. So I can write this as a minus k into x, and I can write this a is equal to minus k upon m into x. If I put the value of this a as d square x upon dt square, I can put the value of a plus k by m, x is equal to 0. Now this is called as the equation of the motion of the simple harmonic motion. Now from this equation you can calculate all the remaining entities like acceleration, velocity and displacement. Now from this equation I can write d square x upon dt square is equal to minus k upon m into x. So this is nothing but the a, so which is nothing but k upon m into x. And we know that this we have considered a new entity omega is equal to square root of k upon m. So I can write this omega square is equal to k upon m. Let me put this value of this omega square. So this will be omega square x. So once you know the equation of the motion, you can calculate the acceleration. Now from this equation you can see that this acceleration is always directed in an opposite direction to this displacement. Now from this equation we can calculate velocity also. Now we know that acceleration is equal to d square x upon dt square. I can write this d square x upon dt square as dv upon dt, and I can write this dv upon dx into dx upon dt. We know that dx upon dt is nothing but v, so let me write this as a dv upon dx. So if I put this value of this a into this equation, we are going to get, so this v dv upon dx is equal to minus omega square x. So if I take this dx on this right hand side, and if I integrate this equation, so taking integration on both the sides, we are going to get, oh, it will be v dv not dx. Okay, so we are going to get this v is equal to minus omega square, that is a constant terms, x square upon 2 plus c. So this will be v square upon 2. Now if I want to calculate the value of this c, I can take the boundary conditions. When this x is equal to 0, or say when this x is equal to plus minus a. So a is the amplitude, and it is a maximum displacement from its mean position, which we call it as the amplitude. So we have taken the amplitude a, and this amplitude a can be positive or negative. Suppose this is a particle, so this is a plus a, and on this side this is a minus a. If I put this value of x is equal to plus a, so at this point the velocity is 0, because we know that once you take the pendulum there and when you release, when it is coming back to the position a, its velocity will be 0 for a moment. Its velocity will be 0, so we can take that as a boundary condition. So when this x is equal to plus a, velocity is equal to 0. Now if I put these two values in this equation, so I will get, so this c is equal to omega square a square upon 2. If I put this value of this c over in this equation, I am going to get this v square upon 2 is equal to minus omega square x square upon 2 plus omega square a square upon 2. So this 2 will get cancelled, and what we are left with is omega v square is equal to minus omega square x square plus a square, or we can write omega square into a square minus x square. So if I take the value of this v, so v will be plus minus omega square root of a square minus x square. So this will be the value of v. From this equation we can see that this velocity can be calculated from the equation of the motion. So let me call this as equation 1. So this is the equation of the motion. From equation of the motion you can calculate acceleration, you can also calculate the velocity. So I will directly write the equation for the velocity over here. So this v is equal to plus minus omega square root of a square minus x square. So let us calculate the displacement from the same equation of the motion. So we have got this equation, v is equal to plus minus omega square root of a square minus x square, and we know that v is nothing but dx upon dt. So I can take this dt on right hand side and this square root on the left hand side. I can write this dx upon square root of a square minus x square is equal to plus minus omega into dt. And if I take integration of the both the sides, so I will get sine inverse of x upon a. So this omega t plus alpha, where this alpha is a integration constant, and I can write that x upon a is equal to sine of omega t plus alpha, and I can write this x is equal to a into sine of omega t plus alpha. So this equation will give us the expression for the displacement in a simple harmonic motion. Now there are also different cases, and we can calculate what will happen if the particle is starting from the mean position, or when the particle is starting from the extreme position. So we can calculate that term also. So when the particle is starting from its mean position, so the displacement is given by x is equal to a sine omega t, and when the displacement is, or when the particle is starting its journey from the extreme position, then that x is given by x is equal to a cos of omega t. So we are calculating these equations by taking different conditions, like when this particle is starting from the mean position, okay, its displacement will be 0, so x will be 0 at t is equal to 0 when the particle is starting from its mean position. So if we put this so when we put this x is equal to 0 and t is equal to 0 in this expression, so what we are going to get is 0 is equal to a into sine of alpha, or we can get this sine alpha is equal to 0, and we can say that this alpha is equal to 0. So when this alpha is equal to 0, we are going to get x is equal to a sine omega t. So this is the expression for the displacement when the particle is starting from the mean position. And when the starting particle is starting from the extreme position, then we can say that this x is equal to plus minus a at t is equal to 0. Now if I put these two values in the equation, so I am going to get plus minus a is equal to sine of omega t plus alpha, a sine alpha. So it will be sine alpha is equal to 1, or I can get alpha is equal to pi by 2 or 3 pi by 2. Therefore, this is nothing but sine of omega t plus pi by 2. It is nothing but the cos alpha. Therefore, this is the expression for the displacement of a particle when the particle is starting from the extreme position. So the moral of the story of this lecture is, once you know the equation of the motion of any system, okay, in this lecture we are going to study the equation of the motion of the simple harmonic motion. Okay, so once you know the equation of the motion of the simple harmonic motion, then you can calculate acceleration, velocity and displacement also. So the moral of the story of this lecture is, once you know the equation of the motion, then you can calculate all the physical quantities related to any system.